Okay, let's dive right into this explainer. Today we're unpacking a genuinely fascinating paper where the ultimate goal is literally using high-level math to rescue an industrial manufacturing process from total physical meltdown. We're going to explore how complex partial differential equations and Laplace-Domain modeling, well, they aren't just dry textbook exercises. They are absolutely critical tools for controlling thermal crosstalk and polymer extrusion. It's this perfect, beautiful blend of physics, advanced mathematics, and highly practical engineering.
So we are essentially looking at a rescue mission today. We're answering exactly how translating physical realities into mathematical frequencies prevents catastrophic equipment failure. When you're manufacturing plastic profile extrusions or spinning out 3D printing filaments, your margin for error is practically zero. We have to rely on abstract math here because physical intuition alone, it just isn't enough to track the invisible thermal forces acting inside solid steel over time.
Let's take a quick look at our step-by-step engineering syllabus. We'll start with the polymer extrusion problem, move into the physics of heat conduction, explore the Laplace-Domain transformation, then building the MIMO matrix, look at the MATLAB simulation and overshoot, and finally wrap up with the MIMO decoupling solution. All right, section 1, the polymer extrusion problem. The crucial thing to understand here is that for semi-crystalline engineering polymers, like LLDPE, which is Linear Low-Density Polyethylene, the temperature window is incredibly tight. Process stability relies on an exact, spatially varying temperature profile spread across a tool steel processing barrel. If our 3-zone extruder is too cold, the machine physically breaks down. The material just fails to flow, you get severe pressure spikes, and that can actually tear apart the drive mechanics. And trust me, nobody wants to explain a shattered gearbox to their boss. On the flip side, if it's too hot, the plastic is structurally ruined. Thermal degradation causes microscopic voids that completely wipe out the material's mechanical strength. The invisible villain behind these massive temperature spikes is something called thermal crosstalk. Basically, it's an uncontrollable heat bleed between the 3 independent sections of the barrel: the feed zone, the transition zone, and the metering zone. You might try tweaking the heat in just the feed zone, but a transient thermal wave is going to continuously bleed right into the adjacent zones, completely trashing that delicate temperature balance we just talked about. Moving right along to step 2, the physics of heat conduction. See, you simply cannot isolate the heat because the machinery is a continuous, solid block of tool steel governed by Fourier's law of heat conduction. Tool steel has specific physical parameters, density, thermal conductivity, specific heat capacity, that basically turn the entire barrel into a continuous differential control volume. Thermal energy doesn't care about the artificial boundaries of our heating zones. It flows dynamically right down that one-dimensional spatial coordinate.
Which brings us to step 3, the Laplace-Domain transformation.
This is where we break down the complex partial differential equation, or PDE. First, we define that continuous PDE using Fourier's law. Second, and here is the clever part, we use integration by parts to map messy time variables into a continuous time Laplace transform. This naturally exposes our characteristic spatial second-order differential equation. Finally, by applying Neumann boundary conditions to represent the heavily insulated casing caps, we mathematically force a symmetrical hyperbolic cosine thermal profile across the internal boundaries. It's just a wildly elegant mathematical maneuver to turn a physical mess into a neat, solvable equation. Think of the Laplace transform as a pure translation. We're moving from the unpredictable, messy physical world into a structured algebraic space where we can actually solve the problem. Instead of wrestling with a continuous, infinite-dimensional physical wave happening in real time, we're just manipulating a clean algebraic equation in the S-domain. Honestly, it's a total eureka moment for the engineering design. All right, step 4, building the MIMO matrix. Now, an operator might look at this and incorrectly assume they're dealing with a simple SISO setup, single input, single output, isolated zones. If you program the controller with SISO logic, you're assuming temperatures change as isolated first-order exponential curves. But the math reveals a deeply coupled MIMO, multi-input, multi-output reality. Because the heat acts as an infinite-order distributed delay line across that continuous tool steel, we have to build a MIMO dynamic transfer function matrix just to track exactly how the thermal energy spatially cross-couples over time. Let's hit step 5, MATLAB simulation and overshoot. A MATLAB simulation is absolutely essential here. Why?
because human brains simply cannot calculate 30 mathematical nodes interacting across 600 seconds of continuous transient phases. The software discretizes the 0.6-meter barrel into 30 spatial nodes and runs an explicit finite difference method. Over an initial 10-minute, so 600-second, transient phase, MATLAB visualizes exactly how the thermal zones drag each other upward. It mathematically proves our analytical model is spot on. The machinery possesses massive thermal inertia and really long nonlinear phase lag. If you ignore the MIMO math and stubbornly run those heaters independently, constructive thermal interference causes a massive overshoot. We're talking about driving the central core to a catastrophic 312.3 degrees Celsius. Remember the LLDPE polymer we mentioned earlier? At 312.3 degrees, you induce rapid, destructive polymer chain scission. You are instantly ruining the mechanical integrity and the aesthetic quality of the plastic. You're basically turning valuable raw material into completely useless scrap.
Finally, step 6, the MIMO decoupling solution. By integrating a decoupling matrix into the control loop, we basically build an active defense mechanism. Step 1, we take our target set points and compare them with back-fed spatial temperature measurements. Step 2, we pass those signals through a parallelized multivariable array, specifically a feed-forward decoupling matrix. And step 3, this allows the system to proactively throttle down adjacent heaters the exact millisecond a neighboring zone begins an operational transition. The paper's ultimate goal is brilliantly realized right here. We are literally using an inverted transfer function to mathematically erase the destructive heat bleed before it ever reaches the plastic. Because the input signals pass through this inverse filter, the physical, structural heat conduction is totally canceled out. The actual temperatures transition cleanly right to their targets, without any localized material degradation. It's amazing. It really leaves you wondering, if translating time into frequency can save solid steel from melting itself and ruining thousands of dollars in polymer, what other hidden industrial threats are just waiting for the right mathematical translation to solve them? Keep an eye out for the invisible math in the physical world around you. Thanks so much for joining me on this explainer.